Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at integration by parts. So what I'd like to do is talk about the product rule of differentiating. So it's something that we've talked about earlier, and we learned that if you have a product of functions, u and v, the derivative of that product will be equal to u times the derivative of v plus v times the derivative of u. What I would like to do is manipulate this to come up with the formula we're going to use for integration by parts. And in order to do that, my first step is multiply by dx. So then I'll have the differential of uv equals u times dv plus v times du. So I just multiplied through by dx. Then I'm going to integrate both sides. When I integrate this side, I'm going to integrate each term. Now the integral of a differential of uv is simply u times v. Then what I want to do is isolate this term. So I'm going to take the integral of u times dv will be equal to, I'm going to subtract this term from both sides, so it'll be u v minus the integral of v times du. And that's what we're going to use to integrate certain types of integrals. Let's take a look at how we use this. In all of the patterns that we've looked at so far, we've had a du factor. So we've had whatever type of function it is, and then we've had a du factor. In these questions, you're going to encounter factors that are not part of the du factor. So for example, if I was asked to find the integral of x times square root of 3x plus 1 dx, I can do it if that x isn't there. Or I could do it if I had, for example, an x squared there, where this would be part of the du factor. But the derivative of what's inside my power is 3. It has no function x. So this is a perfect situation where I can use what's called integration by parts. And what we're going to do is determine what the u is and what the dv is. So there's going to be one of those factors is going to be u, the other factor is going to be dv. Typically you pick u so that the function becomes easier when you take its derivative. So if we take a look at x and square root of 3x plus 1, x certainly gets easier when we take its derivative. This power doesn't. You also have to be aware that when you choose what factor becomes dv, it has to be something that you can integrate. So in this case, I'm going to choose x as my u, which means the rest of this is my dv factor. I'm going to set up a little chart. I'm going to have u, and I'm going to have dv. Now in the formula, I'm also going to have v, and I'm also going to have du. So I'm choosing u to be x. I'm choosing dv to be 3x plus 1 to the power of 1/2 dx. Remember, it's a differential, so it has to have the dx there. Now to find du, I just differentiate. So du, if u is x, du will be dx. And in order to find v, I have to integrate. So v will be the integral of this. So v will be the integral of 3x plus 1 to the 1/2 dx. In order to integrate this, I'm going to use my general power formula. I need the derivative of 3x plus 1, which is 3, which I can introduce as long as I balance it. And now I can use my pattern for general power. So this integral will be 1/3 times 3x plus 1 to the power of 3/2, and I divide by 3/2. I'm not going to bother putting a c in while I'm doing the process. At the very end, once I'm done my integration, then I'll add my constant of integration. So this will be equal to 1/3 divided by 3/2 will be 1/3 times 2/3, which would be 2/9. So that's my v. Now that I've determined all of those values, I plug into my formula. So this integral, u times dv, will be equal to u, which is x, times v, which is 2/9, times 3x plus 1 to the power of 3/2, minus the integral of v, which is 2/9, 3x plus 1 to the 3/2, du, which is dx. Now, if you chose your u and your dv correctly, you should end up with an integral that's easier to integrate than what you started with. Can we integrate this? Yes, we don't have that factor of x anymore. Let's just clean this up first. So this is 2/9 x times 3x plus 1 to the power of 3/2. And to integrate this, again, this is a power. We can move the 2/9 out front. Again, we have a power. We can integrate this power, but we need a du factor of 3 dx. I don't have the 3, so I'm going to introduce it. I will balance it. Now I can use my general power formula to integrate that. So that will be 2 over 27. And the integral of this will be 3x plus 1 to the power of 5/2. And then I divide by 5/2. Now I can put my plus c because I don't have any integrals anymore. And then I'm going to clean this up. We can take 2 over 27, divide by 5/2, which means we multiply by 2/5, and replace this with 4 over 135. Let's try some more examples. In my next example, I have the integral of 4x times e to the 2x dx. We cannot integrate this by any of the patterns that we've looked at. If I didn't have that x there, I would be able to. But that x creates a problem. It's not part of my du factor. When you have a situation like this where you have a product and one of them isn't the derivative of the other function, then one option is to take a look and see if we can use integration by parts. So we have to decide what we're going to let the u be and what the dv will be. So I look at my functions. I have 4x and I have e to the 2x. And when I take the derivative of 4x, it becomes 4. So that becomes an easier function. However, when I take the derivative of e to the 2x, my derivative will be 2e to the 2x. So that doesn't become simpler. So I'm going to try letting u be 4x, which means dv will be e to the 2x dx. To find du, I just take the derivative and then multiply by dx. To find v, I take the integral. So that v will be the integral of e to the 2x dx. I need a factor of 2, so I'll introduce 2 and then I'll divide by 2. So now I can use my exponential form to do the integration. This integral will be 1/2 e to the 2x. Now that I've completed the chart, I'm going to plug everything into my formula. So this integral will be equal to u, which is 4x, times v, which is 1/2 e to the 2x, minus integral of v, which is 1/2 e to the 2x, times du, which is 4 dx. I suggest you clean everything up first. So we have 4 times 1/2 will be 2x e to the 2x, minus 1/2 times 4 is 2 as well. So I'm going to write this as e to the 2x. And I'm just going to leave the 2 there because I do know that I need it as part of my du factor. This is a simpler function to integrate because we can use a pattern that we've taken already. So we started with something that we couldn't use our patterns for, and by doing it by parts, we end up with an integral we can do by our previous patterns. So in order to integrate this, this is our exponential form again. I've got the factor of 2 that I need, so I just simply integrate. So it'll be 2x e to the 2x minus e to the 2x. Now I can add my constant of integration. You can always check to see if we integrated this correctly by differentiating this. And in order to differentiate it, we'd have to use the product rule on this first term. But once you did the derivative and simplified, you should end up with 4x e to the 2x. Let's try another example. Again, we have a product of functions, and one of them is not the derivative of the other. So we're going to try integration by parts. U is the thing that gets easier. When we differentiate 3x, it just becomes 3. When we differentiate sine of 6x, it's 6 times the cos of 6x. So that doesn't become easier. So I'm going to choose this as my u. And dv will be sine of 6x dx. Differentiate to get du, so that would be 3 dx. Integrate to get v. So v will be the integral of sine of 6x dx. This is one of my basic trig patterns. I can integrate that. I just need a factor of 6 here, which I'll balance here. So when I integrate that, it's going to be 1/6. The integral of sine of 6x will be negative cos of 6x. Now I've got my chart complete. I plug into my formula. So this integral will equal u, which is 3x, times v, which will be negative 1/6 cos of 6x, minus the integral of v, which is negative 1/6 cos of 6x, times du, which is 3 dx. And then I usually take the next step to clean it up. So 3 times negative 1/6 is negative 1/2 x cos of 6x. Minus minus becomes plus. The 1/6 times the 3 is 1/2. I'm going to pull it out front. And then I have the integral of cos of 6x dx. We still have an integral, but we have an integral that's going to be easier to integrate than what we started with. This fits our basic trig pattern. In order to integrate this, we need a factor of 6, so we divide by 6. So our result will be negative 1/2 x cos of 6x plus 1/12. The integral of cos of 6x, 6 dx, is sine of 6x. Now I'll add my constant of integration. Let's do one more example. This example is a little bit different because we don't have a product of functions. We actually only have one function, but it's a function we don't know how to integrate. We haven't taken any pattern that allows us to integrate this. So we're going to try this by integration by parts. We're going to use natural log of x as u because this can't be part of the dv factor because we don't know how to integrate it, but we do know how to differentiate it. So we're going to let natural log of x be u, which means dv is just simply going to be dx. If u is natural log of x, when I differentiate, du will be 1/x dx. And if dv is dx and I integrate, v will be x. Now that the chart is complete, let's plug into our formula. U, which is natural log of x, times v, which is x, minus the integral of v, which is x, times du, which is 1/x dx. Clean it up, put that x out front, then you don't need the brackets. Simplify, x times 1/x is just a 1. I now can integrate this. So the integral of 1 dx is just x. So it's a bit of an unusual question because you don't have a product of two functions, but this method allows us to integrate that. I would like to do more integration by parts questions, particularly ones where I have to do integration by parts more than once on an example. So that will be in the next video. When you're ready, I'll see you then.